Okay, in this video lecture, I am going to start Chapter 8, which is titled Chemical Equations and Reactions, and I'm going to cover the first part of Section 1, which means describing chemical reactions. So in this section, we're going to talk about how do you write a word equation, and from that word equation, are you able to write a chemical equation? So the objectives, we'll talk about what are some signs that a chemical reaction has taken place, and then what are the requirements that you need in order to correctly write a chemical equation, and then finally practice writing word equations and formula equations for a given chemical reaction. And then I think we'll spend a good chunk of the next lecture talking about how do you balance a formula in depth. Okay, so a chemical reaction by definition is one or more substances are changed into one or more different substances. And so some good physical indicators that a chemical reaction has taken place is you see light or heat being given off, or maybe that heat is being absorbed. So you definitely have a temperature change, or you see the presence of light. Second physical indicator is a color change in the sample that you are observing. Maybe you utilizing bromothymol blue, and you add carbon dioxide of bromothymol blue, and it turns from blue to yellow, right? That's a color change. Chemical reaction taking place there. Production of gas, so any bubbles or fizzing that you may see. And then the formation of a precipitate, which is a solid that literally falls out of solution. So you will do lots of chemical reactions in this chapter, but one of them, you will take two substances, two clear solutions, and you will pour them into each other, and you will literally see a solid form and fall out of the solution, basically separate from the solution. So I'm going to show you a really cheesy YouTube clip here. It's just 2 minutes long.
Welcome to Moo Moo Math and Science. In this video, I'd like to talk about the indicators of a chemical reaction. Life depends on chemical reactions. Here's a diagram of all the chemical reactions that take place in your body. Some chemical reactions, like this one taking place right now, are obvious. Others are not. So what are the indicators of a chemical reaction? There are at least 5. They are fizzing or bubbles, a change in odor, a change in temperature, a permanent change in color, or a precipitant being created. Fizzing or bubbles are caused when gas is released when chemicals are mixed, like when you mix Mentos and soda. Some chemical reactions cause a change in odors. Sometimes it is pleasant, like the smell of a cake baking, and sometimes they are not. A chemical reaction can cause a change in color. The change in color is permanent. Take a look at the different changes in color from the same cabbage juice when mixed with different chemicals. The color change is different based on the substance that it is mixed with. Next, a chemical reaction can cause a change in temperature. An example is fire is when the temperature increases, but sometimes it'll be a change in which the temperature becomes cold. And finally, a precipitate is created. A precipitate is a solid that settles after mixing certain liquids. So there we go, the 5 indicators of a chemical reaction. Thanks for watching, and Moo Moo Math uploads a new math.
Okay. All right, so the requirements in order to write a chemical equation, or even just reading a chemical equation, first off, the equation you see represents the known facts. Basically, all the reactants and products are identified either through chemical analysis and or the results of the experiments. Number 2, the equation must have the correct formulas for the reactants and the products. Do I have the right oxidation states? Do I have the right charges? Do I have the right symbols? And then this ties into the third requirement, the law of conservation of mass must be satisfied. So on your reactant side, the same number of atoms and kinds are identical to the product side. And if not, then you need to balance it. And the only thing you can really manipulate or change are the coefficients, the numbers in front of the elements or compounds that you are dealing with. So there are types of chemical equations, and we are going to focus in on two of them: word equations versus formula equations. So word equations just means that it's represented by words. It has a qualitative or descriptive meaning. So you can take methane and you add oxygen to it, and it produces carbon dioxide and water. That's it. Okay, so we replace the chemical symbols with words. Methane plus oxygen yields carbon dioxide and water. Formula equations represent the reactants and the products with symbols and or formulas. So this word equation up here, methane plus oxygen, produces carbon dioxide and water. This is what it looks like in formula format. Methane is CH4. I also state the state of matter it is in, gas, plus oxygen, gas, produces carbon dioxide, gas, and water vapor, gas. So some other symbols that are used in chemical equations, you'll see solids, liquids, aqueous, gas. Okay, you'll see the arrow for yields or produces. You might see an arrow with something on top, which means that either you heated it up, or the delta triangle to show change in temperature. Sometimes you'll see a catalyst that was added to kind of get the reaction going. Okay. So when you balance equations, there's a few guidelines. First off, you can only change the coefficients. Okay, this is super, super important. The numbers in front of the element or the compound. You cannot change the subscripts. You just can't. Okay. Polyatomic ions, when you balance them, could be balanced as a unit, but this might not always work. So it might save you some time to group them together as polyatomic, but it just may not work in some cases. So just be aware of that. And then the third guideline is make sure you have the same number of atoms on the reactants as you do on the product side. So here's our first example here. Write word and formula equations for the chemical reaction that occurs when solid sodium oxide is added to water at room temperature and forms sodium hydroxide dissolved in water. Include symbols for physical states in the formula equation, then balance it and give a balanced chemical equation. So first off, let's do the word equation. Okay, so word equation, we have sodium oxide plus, so it says when sodium oxide is added to water at room temperature and it forms, I can't really do an arrow, sodium hydroxide. So that would be like my word equation. And I'm just going to put a big W here to represent word. And slap this over. So on your homework, that's what I'm looking for if it says, hey, write a word equation. Okay. Now we're going to write the formula equation. Okay. So sodium hydroxide, you know what, I'm going to go to my pen on this. So sodium, right, the chemical symbol for sodium is Na, and oxide is oxygen. Okay, so you're like, oh, okay, NaO. Now, before you move on, ask yourself, are the oxidation numbers balanced on this, right? So sodium has a +1. And oxygen has a -2. So my charges don't balance, right? So I got to get a +2 in order to cancel out the -2. So it's actually Na2, okay? Now what's the state of sodium oxide? Oh, it says that it's a solid. So Na2O, parenthesis, little s, plus water. All right, water is H2O. I sure hope you know the chemical formula for water. Now, if it says water vapor, then it would be a gas. If it says ice, then it is solid. So water, by default, is liquid. Okay, at room temperature and forms sodium hydroxide. So sodium is Na, and you're like, oh, what's hydroxide? Oh, hydroxide is a polyatomic ion, and it is OH, and it does have a -1 charge, and sodium has a +1 charge, so the charges balance out, so we are good. We just need one of each. So I have NaOH. Okay, what is the state of sodium hydroxide? Oh, it says dissolved in water. That is key term for, like, another way to say, hey, it's aqueous. It's dissolved in water. Okay, the final thing we got to do is we got to balance this, make sure it's balanced. So I'm going to use a different pen, and I'm going to use red. So when you balance this, okay, you got to make sure you have the same amount on one side as you do the other. So the first thing you should do is take inventory. Okay, so I'm going to write sodium. How many sodium atoms do I have here? Oh, I have 2. And then the next one's listed as oxygen. How many oxygen do I have? 1, 2. And then I have hydrogen, that little 2. So hydrogen's got 2. So I got 2, 2, and 2. So then I go over here. All right, Na, how many Nas do I have? 1. Oxygen, 1. Should be an equal sign right there. Hydrogen, 1. So are we balanced? No, we are not balanced. We got 2, 2, 2, 1, 1, 1. So the only thing you can do to balance chemical equations is to add coefficients. Okay, so that means I can add a number here, or here, or here, and to try to balance these atoms out. So I have 2, 2, and 2. Well, I could easily stick a 2 here, and this 2 would go to the sodium, to the oxygen, and the hydrogen. And now 2 times 1, okay, now I have 2 sodiums. 2 times 1, now I have 2 oxygens. 2 times 1, now I have 2 hydrogens. 2, 2, 2, hey, I'm balanced. I just had to add a coefficient of 2 right there. Translate the following chemical equation into a sentence. Okay. So I might say something like, what's NaOH? Okay, it's sodium +1 charge. OH, that's hydroxide. So when sodium, well, hold up. What does AQ stand for? Aqueous. So I could say, like, when sodium hydroxide is dissolved in water, hint, hint, aqueous, and combined or mixed with, what's this, iron and nitrates. Nitrate's got a, what, -1 charge? I have 3 of them, so this is an iron 3 nitrate. Iron, Roman numeral 3, nitrite? Nitrate? I think it's nitrate. Combined with, maybe I'm just going to say aqueous, iron 3 nitrate. It produces iron oxide, right? Iron oxide, solid iron oxide. Charge on iron, it's got to be 4, it looks like. Iron hydroxide. And sodium nitrate. Okay, I'm sorry, I have to look this up. I want to make sure that NO3, and I should know, but you know, I always get nitrates and nitrites mixed up. Nitrite is NO2, so it's not nitrite. It is nitrate. Okay. See, good thing I double checked. Nitrate. Sodium nitrate. Okay. And sodium, well, what's the state of sodium nitrate? Aqueous. Aqueous sodium nitrate. Cool. Okay. So is that a sentence? Yeah, that's a sentence. If I am I able to use this sentence to figure out my chemical formula from it? Yeah, I think so. So, looks good. Right word and balanced chemical equations. All right. Solid calcium reacts with solid sulfur to produce sodium calcium sulfide. So let's do the word. Whoops. I had it queued up. Let's just see. Yep. Did that one right, guys. Woohoo. Okay. Just gotta use it. So, write the word. Let's do the word. Calcium. Metal, I guess. Plus sulfur. Produces calcium sulfide. Cool. Did that one right. Now we got to do the formula. So I'm going to get a pen. Solid calcium, so Ca. And it says solid, so I'm going to put S in parentheses. Reacts with solid sulfur. Symbol for sulfur is S. It is also solid. Produces calcium sulfide. So the charge on calcium is a +2. What's the charge of sulfur? -2, so it's just one of each. And what's the state of calcium sulfide? Solid. There, that's it. Now is it balanced? I have 1 calcium here, 1 sulfur here, over here, 1, and 1. Yeah, that looks balanced to me. Okay. Example 4. Hydrogen gas reacts with fluorine gas to produce hydrogen fluoride gas. Okay, so word equation. Hydrogen gas plus fluorine gas produces hydrogen fluoride gas. Or I guess I could just leave it hydrogen fluoride just because you need the gas here because hydrogen, you just can't have H by itself. So it's going to be bonded to another H for hydrogen gas. So we learned that a while ago, a different chapter ago. So let's just double check my work here with the word equation. I left the gas, but okay. All right, so now the formula. So hydrogen gas is H2, and the state of it is gas plus fluorine gas, so that's going to be F2, that is also gas, G, produces hydrogen fluoride, so hydrogen's got a +1 charge, fluoride, fluorine, -1, so I just need 1 of each, and it's a gas. Is it balanced? So over here, how many hydrogens do I have? 2. How many fluorines do I have? 2. Over here, H, I have 1 H and 1 F. It's supposed to be an F. So they're not balanced. So the only thing you can change when you try to balance it is the coefficient. So it means I can add a number here, here, or here. So I have 2, 2, 1, 1. Well, if I stick a 2 here, that 2 will go to the H and to the F. So now I have 2 hydrogens and 2 fluorines. So then that would make me balanced. Okay, the next example. Solid aluminum or aluminium metal reacts with aqueous zinc chloride to produce solid zinc metal. I feel like I'm missing some information here, so let's look at this. So solid aluminum plus zinc chloride produces zinc. Now, already I can tell this is, you need to fill in the gaps here. So zinc is taken care of. Remember, with the law of conservation mass, whatever you have on one side, you better find evidence for the other side, right? So zinc is here and here, but I'm missing aluminum chloride. So that must mean that aluminum and chloride are bonded together, okay? So aluminum chloride. Yep. Okay, so then now we have to write a formula. So aluminum, the symbol is Al, and it's solid, so S, plus zinc chloride. Let's just say zinc has a +2. So how many chlorines? If this is a +2, how many chlorines am I going to need? If chlorine's a -1, I'm going to need 2 of them. So CnCl2. And it says it's aqueous. So aqueous means AQ. All right, produces zinc plus aluminum chloride. So zinc, and it says solid zinc metal. So that is solid. And then aluminum chloride. Aluminum has a +3 charge. Chlorine has a -1. So how many chlorines am I going to need to balance out the charge on aluminum? 3 of them, right? So AlCl3. And I don't know the state of this, but my guess would be aqueous. So I'm going to make sure that the homework assignment doesn't give you something like that. Okay, so now the next thing is it balanced? So we're going to take inventory. Aluminum, I have 1. Zinc, 1. Chlorine, 1. Oh, mistake, 2. Aluminum, 1. Zinc, 1. Chlorine, 3. Okay, so my aluminums and my zincs are good. It's my chlorines that are not. And remember, you can only change the coefficients. So numbers in front of here, 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 or here. So looking at 2 and 3, there's a strategy called odd and even, where you think of a number where they both go into, okay? So 2 and 3, the least common number they both go into is 6. So how many times would I have to multiply chlorine, ZnCl2, to get to 6 chlorines? Well, that would be 3, okay? So when I do this, 3 times 2 is 6, but this 3 also changes my zinc number, okay? So you put a 3 here. Then you come back over here, and you're like, okay, well, I got 3 zincs, so I can put a coefficient of 3 here, so that stays balanced. And then what's a common number that both, what do I have to multiply, chlorine to get to 6, right? So 3 times what equals 6? 2. So when I put that coefficient here, oh my gosh, it changes the aluminum. And then 2 times 3 is 6, chlorine. So am I balanced here? 1, 3, 6, 2, 3, 6? No. But that's okay. This is an easy fix. I can stick a coefficient in front of that aluminum. And now I am balanced. Woohoo! What a process, right? Okay, so that does it for notes today.